Hi all. നമ്മൾ ലാസ്റ്റ് ക്ലാസ്സുകളിൽ ഡിസ്കസ് ചെയ്തത് അരിത്തമെറ്റിക്കൽ ഫങ്ഷൻസിനെ കുറിച്ചാണ്. അരിത്തമെറ്റിക്കൽ ഫങ്ഷൻസിന്റെ ഡെഫിനിഷൻസും ഡിവൈസേഴ്സ് ആൻഡ് ഫോർമുലയും പിന്നെ രണ്ട് അരിത്തമെറ്റിക്കൽ ഫങ്ഷൻ ഇമ്പോർട്ടൻ്റ് ആയിട്ടുള്ള രണ്ട് അരിത്തമെറ്റിക്കൽ ഫങ്ഷൻസ് ആണ് ഓയിലർ ടോഷ്യൻ ഫംഗ്ഷനും പിന്നെ മോബിയസ് ഫംഗ്ഷനും. അവ തമ്മിലുള്ള രണ്ട് അവയുടെ ഡിവൈസേഴ്സ് ആൻഡ് ഫോർമുലയും പിന്നെ അവ തമ്മിലുള്ള റിലേഷനുമാണ് നമ്മൾ കഴിഞ്ഞ ദിവസം സെക്ഷൻ 2.4 വരെയുള്ള സെക്ഷൻസിൽ നമ്മൾ ഡിസ്കസ് ചെയ്തത്. ഇനി ഇതിൽ നമ്മൾ ഈ സെക്ഷനിൽ നമ്മൾ ചെയ്യാൻ പോകുന്നത് 2.5ഉം 2.6ഉം ആണ്. 2.5 എന്ന് പറയുന്ന ഒരു പ്രൊഡക്റ്റ് ഫോർമുലയാണ്, അല്ലെങ്കിൽ ഓയിലർ ടോഷ്യൻ ഫംഗ്ഷൻ ഇവാലുവേറ്റ് ചെയ്യാനുള്ള ഒരു ഫോർമുലയാണ്. ഫോർമുല ഓൾറെഡി നിങ്ങൾ ചെറിയ ക്ലാസ്സിലൊക്കെ പഠിച്ചിട്ടുണ്ടാവും. പക്ഷെ അത് പ്രൂവ് ചെയ്യുന്ന അരിത്തമെറ്റിക്കൽ ഫംഗ്ഷൻസ് നമ്മൾ പഠിച്ച മൊബിയസ് ഫംഗ്ഷൻസിന്റെ ഒരു പ്രോപ്പർട്ടി ഉപയോഗിച്ചാണ്, അല്ലെങ്കിൽ മൊബിയസ് ഫംഗ്ഷനും ഫൈയും ഉപയോഗിച്ചിട്ടുള്ള ഒരു റിലേഷൻ നമ്മൾ പ്രൂവ് ചെയ്തതിൽ നിന്ന് നമുക്കിത് ഈ ഫോർമുല പെട്ടെന്ന് ഡിറൈവ് ചെയ്തെടുക്കാൻ പറ്റും. 2-3 സ്റ്റെപ്സിൽ ഡിറൈവ് ചെയ്തെടുക്കാൻ പറ്റും. അത് കാണിക്കാൻ പറ്റുള്ള ഒരു പ്രൂഫ് അതിനകത്ത് കൊടുത്തിട്ടുണ്ട്. അപ്പോൾ ഇതൊരു തിയറമായിട്ടാണ് ഡീൽ ചെയ്തിരിക്കുന്നത്. അപ്പം ഫോർമുല നോക്കാം. ഫോർ n greater than or equal to 1 we have phi of n is equal to n times product p divides n. P is the prime number, prime divisor of n, 1 minus 1 by p. The proof പറയുകയാണെങ്കിൽ if n is equal to 1 the result is trivially true if we consider that product part in the right hand side as 1, then this formula easily follows. For n greater than 1 we assume p1 p2 pr are the distinct prime divisors of n. Then this formula can be derived in such a way that we start with the product in the right hand side. Product p divides n 1 minus 1 by p, that is equal to product I equal to 1 to r 1 minus 1 by pi. As we assumed p1 p2 pr are the distinct prime divisors of n. Then this product can be expanded like 1 minus summation 1 by pi plus summation 1 by pi pj minus etc plus minus 1 raised to r divided by p1 p2 etc pr. That means the sign depends on the factors in the denominator, and this can be considered as sigma d divides n mu of d by d. If we consider all the divisors of n, we can insert 0 in that summation. So mu of d by d will give 0 if d is a divisor which is not square free. Then this summation d divides n mu of d by d can be written as 1 by n times summation d divides n mu of d times n by d. അവിടെ ചെയ്തൊരു n insert ചെയ്തു, multiply n divide by n, then you can make that summation as 1 by n times summation d divides n mu of d n by d, and the summation in the last expression will give the relation between mu and phi, so that can be replaced by phi of n by n. So this will follow the above formula. Now we can see some consequences of the formula we have derived. The properties are, the first one is phi of p raised to alpha. That means if that number has only one prime divisor, then that value phi of p raised to alpha is equal to p raised to alpha minus p raised to alpha minus 1, and phi of mn equal to phi of m into phi of n into d divided by phi of t, where d is the GCD of m comma n. The third property, phi of mn is equal to phi of m into phi of n if m comma n is equal to 1. Actually that is a special case of property 2. If GCD of m comma n is equal to 1, then d by phi of d term will yield 1, then you will get phi of m times phi of n. The fourth property, a divides b, implies phi of a divides phi of b. In phi we have seen phi of n is even for n greater than or equal to 3. If n is equal to 1, phi of 1 is defined as 1, that is an odd number. And for phi of 2, we have phi of 2 is equal to 1, that is also odd. For any other positive integer, we have phi of n is even, that's importance of the property 5. Moreover, if n has r distinct odd prime factors, then 2 raised to r must divide phi of n. These are the 5 properties or 5 consequences of the above or previous formula for phi of n. Then we can see the proof. These are all one line or two line proofs. For the first part, we directly apply the formula that we have seen in the previous slide. P of phi of p raised to alpha is equal to p raised to alpha times 1 minus 1 by p. That is equal to p raised to alpha minus p raised to alpha minus 1. For the second, phi of mn by mn, we evaluate first phi of mn by mn. Phi of mn by mn can be written as product p divides n 1 minus 1 by p product p divides m 1 minus 1 by p whole divided by product 1 minus 1 by p. That means the first product, in the first product we consider all the distinct prime divisor of n. In the second, that means in the second, in the numerator, we consider all the uh, prime divisors of m, and in the denominator we consider only the prime divisors of d. So phi of mn divided by mn can be written in this manner. Uh, that is because by the above formula we know that what is phi of n? Phi of n is nothing but the product of some terms. Each term contains 1 minus 1 by p, where p is the divisor of that n. So here we use we need to use the distinct prime divisors of mn. Okay, so for the distinct prime divisors of mn, we consider the distinct prime divisors of m as well as the distinct prime divisors of n. So if we consider all those product, there must be some repetitions. We would consider prime divisor for mn twice in the consideration of prime divisors of n and prime divisors of n. So we need to remove the repetition. So we will consider the common prime divisors of n comma m. For that we consider all the prime divisors of GCD of mn. Okay, the denominator stands for that part. So the first product can be written as phi of n divided by n, phi of m divided by m is the second product. The denominator we have phi of d by d. So by simplification we can write phi of mn by mn is equal to phi of n into phi of m uh, into d whole divided by mn. Then by cancelling m comma n, we can get the formula. I have already said that the third one is nothing but the consequence of second one. For the fourth is one of the important properties of phi. If a divides b, then phi of a divides phi of b. If I follows the same relation, if a is a divisor of b, then phi of a is a divisor of phi of b. Phi follows the same relation. For that we consider first we consider suppose a is a divisor of b, then b can be written as ac for some integer c in between 1 and b. If c equal to b, then a must be 1. And part 4 is the fourth result is easily follows. Therefore we assume c less than b. Okay, if c less than b, we can write phi of b is equal to phi of ac, that's equal to phi of a, phi of c, d by phi of d, where d is the GCD of a comma c. This is by 2. Now we will use mathematical induction for b is equal to 1, 2, 3, etc. So for b is equal to 1, the result follows. For b and we for the mathematical induction hypothesis, we assumed that uh, the result follows for every integer which is less than b. Okay, then we will prove the result is true for uh, B itself. Okay, so now consider uh, this result is uh, this result is true for every integer less than b. That means if we consider an integer c which is less than b, then d divides c implies phi of d divides phi of c. That's the induction hypothesis. Then how we prove this? Okay, then you consider phi of b is equal to phi of ac, that is equal to phi of a, phi of c, uh, d by phi of d. In that, we can rearrange that as phi of a into d into phi of c by phi of d. Okay. By induction hypothesis, this phi of d divides phi of c. Then we will get phi of c is a multiple of phi of d. Clear? Then that can be written as phi of a times an integer. Okay, that follows phi of a divides phi of b. Okay, that is the proof for 4. Now, the fifth part, we need to prove that phi of n is even for every n greater than or equal to 3 first. So we assume n contains only a even prime divisor, that is equal to n is equal to 2 raised to alpha. Clearly phi of n is equal to 2 raised to alpha minus 2 raised to alpha minus 1 using the part 1. And we assume n contains at least one odd prime divisor. Then phi of n can be written as, using the formula phi of n, uh, phi of n is equal to n divided by p1 p2 p3 etc pr. That is product. In the denominator we have the product p divides n p. Is if p1 p2 etc pr are the distinct prime divisors of n, then that denominator is nothing but p1 p2 etc pr into product p divides n p minus 1. This is obtained by simplifying the formula. Just take the LCM and simplify. Then if you consider our assumption is n has at least one prime divisor, then for that corresponding to that prime divisor we have p minus 1 as an even number. Okay, then this must be a even number because every prime divisor of n divides n. So the denominator n by product p divides n, p is always an integer. Therefore phi of n must be an even number. Now, suppose we have r distinct odd prime factors, then from the product in the right hand side, we can collect r2s. Okay, that means 2 raised to r can be taken out from the product. Now the result 5 follows. Now we move on to section 2.6, the divisional product of arithmetical functions, or we can say we will going to uh, we are going to see the structural properties of arithmetical function. That's a better word. First, we can see a definition. If f and g are two arithmetical functions, we define their trivial product to be arithmetical function defined by h of n is equal to sigma d divides n, f of d g of n by d. We have some remarks about this formula or definition. This product is also known as Dirichlet convolution, and we write h is equal to f star g. This is the star is the notation for Dirichlet convolution or Dirichlet product. So actually, from this definition itself, we can see this h is a binary operation on the set of all arithmetical functions. So set of all arithmetical functions together with this Dirichlet convolution uh, form a group or Poisson group. Okay, now we can see a theorem which states the properties of this digital product. In this, we asserted two properties: f star g equal to g star f, which is nothing but the commutativity of the digital product, And secondly, we have f star g star k is equal to f star g star k. This is the associativity of the same. For the proof, we consider the Dirichlet product or convolution f star g of n is equal to sigma d divides n f of d g of n by d. That is equal to sigma. This summation can be rewritten as a into b equal to 1. Sorry, a into b is equal to n f of a into g of b. അതായത് ഇപ്പോൾ ഒരു ഡി ഡിവൈഡ്സ് എൻ എന്ന് പറയുന്ന ഡിവൈസർ എടുത്ത് എഫ് ഓഫ് ഡി ഇൻറ്റു ജി ഓഫ് എൻ ബൈ ഡി വാലുവേറ്റ് ചെയ്യുമ്പോൾ സിൻസ് ഡി ഇസ് എ ഡിവൈസർ ദെൻ എൻ ബൈ ഡി ഇസ് അനദർ ഡിവൈസർ and their product makes n. Okay, so this summation can be written as a into b, or by putting d is equal to a, then you can return n by d as some b with the property that ab is equal to n. That's the only thing. So this summation can be replaced by this the summation a times b equal to n f of a into f of b. So this a and b vary over all positive integers whose product is n. This makes the commutative property, because we can write f of a into g of b is equal to g of a into f of b. Okay, both are same, or g of b into f of a. Okay, so the commutativity easily follows from this summation. For the associativity, now we will consider d star k is equal to some capital A. Then f star capital A can be considered as f star g star k. Then we start with f star a of n. We need to prove that what is f star a of n? That is f star g star k. So we need to prove that associativity holds. For this, we will write sigma a times d is equal to n f of a into a of d, and this a of d, a is nothing but d star k. So that is a of d is equal to g star k of d. So g star k of d can be written in the format summation b times c equal to d g of b into k of c. Yeah. So we can write it as sigma a times b a into b into c equal to n f of a g of b k of c. Yeah. So this can be associated in any manner. Clear? So associativity follows. Now, now we have uh, we, we will introduce some other arithmetical functions which plays an important role in this structural properties of arithmetical functions. This I of n is very important one. This is called the identity function. I of n is nothing but that in greatest is a part of 1 by n for all n belongs to n. We know that this is nothing but 0 when n is greater than 1 and n is equal to 1. We have this value is 1. Okay? We have already seen this function in is a part of 1 by n in the divisor sum formula for mu of d. Uh, Next is a theorem. For all f, we have f star I equal to I star f is equal to f. So as far as this digital product is concerned, this I can act as an identity. That's why this I is called the identity function. Actually, this is the identity function for this arithmetical functions with respect to digital product. The proof is very simple. F star I of n is equal to sigma d divides n f of d I of n by d. By definition, I of n by d is greatest in the part of n by d. Greatest in the part of 1 by n by d. That is greatest in the part of d by n. When we expand the summation for the values d divides n, the first value we put d is equal to n. Okay, then for that term we have f of n. Because for d is equal to 1, the integral part of d by n is 1. So that term is f of 1, f of n. Then all other terms are 0. If we consider any d which is not equal to n, then that d is always less than n. Clear? So d by n is always a fraction, then in part is always 0. Then rest of the terms are 0. So f star I can be written as f itself. Okay. Similarly, you can prove the other equality, but in fact this divisional product is commutative. We need not prove in the other way around. Then, so using the commutativity, we can state that I star f is always equal to f. This is up to the two sections 2.5 and 2.6. Okay, in the next sessions we will see the different properties, structural properties of these arithmetical functions. That means ഈ arithmetical functionsന്റെ കളക്ഷൻ എല്ലാം നമുക്കൊരു ഗ്രൂപ്പ് സ്ട്രക്ചർ കൊണ്ടുവരാൻ പറ്റുമോ, അല്ലെങ്കിൽ കമ്മ്യൂട്ടേറ്റീവ് ഗ്രൂപ്പ് ആക്കാൻ പറ്റുമോ, അങ്ങനെയുള്ള സ്റ്റഡീസ് ആണ് അടുത്ത സെക്ഷൻസിൽ നമ്മൾ കാണാൻ പോകുന്നത്. ഓക്കെ, താങ്ക് യു.